Hello. This week we will be working on Lab 10, Diffraction and Interferences. So in this lab, we will be provide you with the data that we already collected with the measurements, where it will help you to complete the lab report with understanding of the theory. In this video, I will walk you through the experimental procedure and also go over the available data and spend a little bit time on the pre-lab questions and the application questions. So I hope this will help you to understand the concept and complete the lab report nicely. Well, if you were really in the lab, and I wish we would have, so it is a really nice lab and a cool lab where you can observe nice fringe patterns. Unfortunately, we don't have that opportunity, but I'll show you the data or the fringe patterns that we have observed. So in the lab, you will be given with three items: red laser, the diffraction plate, and a screen. So the screen and the diffraction plate located about 2 meters apart. So the distance from the slit to the screen will be 2 meters. And then what is a diffraction plate? It will be something like this one. When you are looking at it with the naked eye, actually we cannot see the fringe patterns clearly, but if you are very careful enough, you should be able to see some opening slits over here. So in this lab, we will be using the slit pattern at C, which is a single slit pattern with the slit width of 0.16 millimeters. And then also we will be using the slit pattern at D, which is a double slit pattern with the slit width of 0.125 millimeters. And also we will be using the slit pattern at E. Again, it is a double slit and the slit width is 0.250 millimeters. So all these values, the A value and the D values for the double slit, are the given theoretical value. So in the experiment, what we're going to do is we're going to observe the fringe patterns that created by each slits, and then we do some measurements and we're going to calculate the slit widths using the data experimentally. And then you're going to compare that experimental value with the given theoretical value. So let's move on to the single slit experiment. So you will be given with the single slit with the slit width of 0.16 millimeters. And in the lab manual, you should be able to see this picture as picture A, where the slit width is symbol with letter A, right? So when we are having that single slit in front of the laser light, here in this picture, the red lines represent the laser light rays. And when the light rays enter into the single slit, it gets diffracted. So this is a good example of light behaving like a wave. If it is not a wave, the light cannot do a diffraction, because just imagine that if you are rolling a tiny ball through this slit, then the ball will go straight, like it will travel straight. But here, this light just create a pattern by doing diffraction. So this experiment or the light ray pattern represent the wave quality of light. Well, so in this experiment, when we send the laser red light through the single slit, we were able to observe a nice fringe pattern on the screen. So you can imagine the room is really dark. We keep the dark room and we will be seeing or observing really nice pattern on the screen. There will be a little bit focusing going on. So if you are really doing the lab, we need to focus the laser light to the single slit and also adjust the screen location a little bit to get a better focused fringe pattern. Anyway, so if you were able to do those, we should be able to see a really nice pattern like this one. So here at the center, Do you see like it is really bright? That means it has a high intensity than the other locations. So we call this as the central maximum. That is the central maximum. And if you remember your theory about this single slit diffraction, so generally we can write an equation for the dark fringes that occur. So m lambda is equal to a sine theta. So these dark fringes follow this equation. M lambda is equal to a sine theta. Let's imagine we don't know anything about this theory. Anyway, if you notice this nice pattern, we can go over on that one and compare this equation. So what is m and what is lambda? So you know lambda is the wavelength of the light. So here we are using a red light beam. So red light is in the range of 650 to about 700 nanometers. So let's say the wavelength of this used red light is about 650 nanometers. So we know the lambda because it is a quality of the light that we are using. And then A is the size of the slit. This A, it is 0.16 millimeters in our experiment. And M, that is the important factor over here. So M is the fringe number. Which fringe number? There are so many fringes, right? So here, let's say that's the central maxima. And over here, do you see a dark spot? And then again, a bright spot and another dark spot. Another bright one, another dark, right? So this dark spot, the first dark spot that you're observing right after central maximum, that is the first order minimum. So here, it is the first order minimum here. And also here you see a first order minimum. So you see the first order minimum on the both sides of the central maximum. So we say M, the order number, can be either positive one or a negative one. Then likewise, when you pass the second maximum, you see a second order minimum, right? This is the second order minimum and you're observing second order minimum on both sides of the central maximum, right? This is the second order on the left side and that's the second order minimum in the right side. So that M is equal to plus or minus 2. Likewise, you can observe the dark spots all the way to this corner. The intensity is going dimming, right? Its intensity gets decreases, but still there are a number of M's orders over here, right? So in the intensity curve, you may see like the central maxima does have a high intensity, but later it is dimming out. The intensity gets smaller and smaller, but still there are dark spots over there. So in the lab, if you were there and if you're measuring the values, you would not see the intensity curve, but this is what you would have observed. So you are observing just the fringe pattern. So here, in this picture, if we go back to this figure, there are some other things that we need to know. The XM, what is XM and what is L? So clearly we know L is the distance between the slit and the screen, which is 2 meters in our experiment. And XM is the distance from the center maxima to each minima. So M represent any of these numbers, either plus or minus 1, plus or minus 2, plus or minus 3, right? So XM is the distance from the central maximum. So here's the central maximum, and if you take the center of the central maximum, so somewhere here, and the distance from that center to the first minima, here, the first minima, right? So that distance is represented by XM. So if you are measuring the distance to the first order, that will be X1. Then if you measure the distance from the center to the second order minima, that will be X2. So likewise, that is what we're going to measure. So we can, likewise, we can measure the X values for each dark spots or the minimum order. All right, then again, we'll go back to the theory. So as you notice, the L, the distance from the screen to the slit is really larger than the size, the length from the central maxima to first minima, right? It is really tiny. So we can apply the small angle approximation. Here, what is small angle approximation? So here, let's look at this diagram there. So it is a right triangle, and we know like this angle we're going to label is as theta. that's theta. The name of the angle is theta, and here L is the adjacent to the theta, and xm is the opposite to the theta, right? So you can write trigonometric functions like tan theta, sine theta, cosine theta. So if you write the equation for tangent theta, the tan theta, it will be opposite over adjacent. So here's the theta and opposite is xm, and the adjacent is L. So the tan theta value is xm over L. But if you write the equation for sine theta, it will be opposite, which is xm over the hypotenuse. But here, as L is really, really larger than xm, we can imagine or make an approximation that we assume that the sine theta also equal to xm over L. Imagine like this is really, really long. So this value getting smaller and smaller comparatively. So the adjacent, the hypotenuse is about the same as L. So we're going to make that approximation. So you can imagine like it is not like 100% correct or 100% equal, but it is an approximation for our calculations, right? So here we can write that tan theta is xm over L, and that's equal to sine theta. So you know, like why we are interested in sine theta? Because our first equation over here for the dark fringes, m lambda is equal to a sine theta. So if you know the sine theta value, then we can write a really nice, cool equation for m lambda, right? So let's substitute that sine theta with xm over L. So we get m times lambda is equal to a times sine theta. Now sine theta is xm over L. Here you go. So m lambda is axm over L. Let's say I want to solve for a. I can simply solve that, right? So the a will be m lambda times L over xm. M lambda L over xm. So the slit width of the single slit is given by the m, which is the dark fringer or the order number of the dark spot, and lambda is the wavelength of the light, which is red light wavelength, and L is the distance from the screen to the slit, which is 2 meters, and xm. So experimentally we're going to measure this value. So x1, then m equal 1, at m equal 2, m is equal 2, and xm you can measure it. So in the given data sheet, you should be able to see a picture like that, like this one. So this is our observation for a single slit diagram. Maybe in this picture, the intensity is really, really low. So you can't see the dark fringes over here, but we observed that. So we did the measurements for you. As I mentioned, L is 2 meters, and we are going to use this equation to calculate A for each M value. M0, that's the central maximum center point, and the M1, when M equal 1, the distance from the center maxima to the M1 is 9 millimeters to the right. So XMR is 9 millimeters. Similarly, XML for the first dark spot is 9 millimeters. So you may calculate A value for the first order. Then for the second order, the value again given, the distance values are given. So you should be able to calculate A for each dark orders, right? So the data sheet is available on Blackboard. Please download that and use that one instead of just watching this video. So theoretical value is 0.16 millimeters, but please do the calculations to see what you get for the real data. So it might be a little bit offset because we are doing an approximation, and also we do the measurements. Like you see, like here, we cannot really say which place is the center of the first order minimum, right? So we might be making error measurements over here. I mean measurement errors, I'm sorry, it's measurement errors when we are locating the positions of the order minimas and also the central maxima. So because I don't have an intensity graph here, so the highest intense point might be a little bit offset in my mark, right? So that will give some error percentages into the experiment, but that is the uncertainty in the experiment. Well, move on to the next part. So maybe you have learned this already in the class, the Young's two-slit experiment, or we say Young's double-slit experiment. So representing that, or to get an idea about this experiment, we are using two double slits with different sizes. So double slit D, which has a theoretical slit width of 0.125 millimeters, and slit E with the slit width of 0.250 millimeters. So here's the picture on your lab manual. So D is the distance between the two slits, and then XM, again, the distance from the central maxima to the first minima, second minima, third minima, so likewise for each order number, and L is the distance from the slit to the screen. So as I mentioned, you were given with this red laser light and the diffraction grating with all these slits, and then the screen located 2 meters away. So when you light up the double slit, it is interestingly, you will be seeing a different pattern than what you observe for the single slit. So you see, like, here's a fringe pattern, and then another fringe pattern. So we see in envelopes of patterns, right? So here's one envelope, and here's the second one, and another one, third one. Now this is called the central fringe, and here we see, like, it's closely spaced fringe. That's due to the interference of light from the two slits. Now here, these ones, here, this one is the minima and another minima over here. That's the central fringe, and this is the first fringe and the second fringe, right? So that big pattern happens due to the diffraction, right? So here, widely spaced fringes due to interference of light from the two single slit, right? Now, in the experiment, we are not going to bother about the big pattern over here, like due to the diffraction, but we will be looking at this first one, the central maximum. So central maximum intensity, if you draw the intensity graph, it should look like that. So you see a central fringe maximum, and this first order and the second order maximum, right? So we are going to concentrate only on this central fringe, that range. Well, so in generally, again, we can write the equation for the dark fringes. It's m lambda equal d sine theta. Here, it is the same equation as we used the for the single slit, but only difference is here, instead of a, we have d. D is the distance between the two slits, and m, again, changing from plus or minus 1 to any number up here. So here, the central maxima, and then we're going to measure the distance from there. So we are using only this fringe, and central is somewhere here. So we're going to measure the distance from the central maxima to first minima, likewise. Then again, we can apply the small angle approximation, because the slit distance from the screen is larger than the distance from central maxima to first order minima. So again, instead of using tan theta, we can use the sine theta there as xm over L. Then you can substitute that number onto the first equation here, and you can solve for d. D is the distance of the slits. So, or we call this as the slit width of the double slit, is given by m lambda L over xm. Again, the same symbols that we use in the for the single slit. So if you know the fringe order number, and then the wavelength of the light that you used, and the distance to the screen, and the distance from the central maxima to the dark order, then you should be able to calculate D. So that's what you're going to do. So you're going to calculate D using the given data. So in the data sheet, you should be able to see two pictures like this. One is for the double slit at D location, which is 0.125 millimeters. So here again, the central maxima, as I mentioned, we are only considering about the central maxima, and here we have the expanded picture of that central maxima, and all the given numbers are measuring from the central maxima to the first minima, and the second one is to the second minima, likewise, right? So the values are measured in millimeters. So when you're doing the calculation, please be mindful about the units, because wavelength is given in nanometers, and the distance, or the xm, is given in millimeters. So when you're substituting the numbers, you should be able to consider that. Okay. So this C over here, it is just, please ignore that. I think it's a typo. So the D value is m lambda L over xm. All right, so let's look at the pre-lab and discussion questions. So the first pre-lab question is kind of theoretical, and you're going to analyze the given equation just to get an idea about the equation given. So xm is equal to m lambda L over A. So that's the equation for a single slit diffraction of the location of the dark spots on the screen given by this equation. So using this equation, they're asking you to analyze what happened if alpha is increased to the xm value. So you're increasing the lambda. So lambda, that means you're changing the light that you're using. So let's say you're using red light, blue light, yellow light, or green light. So lambda can be varying. Now, what happened if lambda is increased to the what happened to the dark spot location if you increase the lambda? So you're using, in this equation, lambda is on the numerator. So if you increase or having a higher number in the numerator, what happened to the value? Then L is increased. Again, L is in the numerator. So you're increasing the numerator. What happened to the values? Then A is increased. A is in the denominator. So if you increase the denominator, then what happened to the value? So you have a larger number here, then this will go down, right? So you just analyze the equation to get an idea about the relationship. Then in the second pre-lab question, here it's going to use two different wavelength light. So red laser with wavelength of 650 nanometers and the blue laser with wavelength of 405 nanometers. So here you don't need to do any calculations. Conceptually analyze this problem, right? So basically D is given by m lambda L over xm, and lambda red is larger than the lambda blue. So lambda red is larger than the lambda blue, right? Blue is 405. I'm sorry, it's not red, it's blue. So in that case, what happened to D red compared to D blue? Again, my typo. So red, it's not red, it's blue and blue. So you compare the lambdas and then compare the D values. Okay, let's look at the application question. The first one is you to analyze or understand about applying the small angle approximation. So you may either use your lecture slides and understand it, or you can use what I explained above in this video. And in the question 4, it's asking another application question. So again, you may use this equation where the distance is given by m lambda L over xm, and then understand what are the given information. So m is given as 1 and the xm also given as 1 meters. Now see, the units have changed, it's meters, and lambda, the wavelength of the light, is given, which is 633 10 to the power minus 9 meters, right? And then L is 2 meters, you may use that, and then you calculate D. Okay, so I hope this video is helpful for you to complete the lab successfully, and happily this is your last lab for the semester. So congratulations, you have completed one part in the real lab setting, and they had the second part in online format. So congratulations, and I'll see you in the next semester sometime.